Okay, so we're going to jump back in and we're going to continue on with another sample problem. And this one is going to be 16.4 on page 1129 in your book. Now, we'll look at the problem statement here because I think it's a little clearer than underneath my camera. But what we have here is we have a pulley, but the pulley has two places on it that it has weights, so you see weight B and weight A. And they're hanging off of this pulley. Now, as we see the arrangement, what you have to kind of visualize is that this is not like a flat disc, okay? So I would envision that this part where B is coming off of is this string is in a groove on that pulley. And if you would, that is like coming out of the page at us or out of the screen at us, okay? Depth-wise. Then the back part would be going back into the screen, depth-wise, and there would be a groove here that the string would be riding on for our weight A, which is 5 pounds. Okay, so those are hanging off of. So this is not a flat, like uniform disc that we're dealing with. This is like a pulley that has, kind of two different sections with a groove for the strings or the cables to ride in. Now, what it says here, it says that the pulley itself weighs 12 pounds. Okay, so the whole thing with the, that it's sitting there, it weighs 12 pounds. And it has a radius of gyration of 8 inches. Okay, 8 inches. So that's that K value that we talked about earlier. And it's connected to two blocks as shown. Okay. Assuming no axial friction, determine the angular acceleration of the pulley itself and the acceleration of each one of the blocks. Okay, so let's go underneath our camera. This is the problem statement that we just read, and I'm going to go underneath and kind of get started with my knowns, my unknowns, and we'll draw a little diagram here with the information that we've been given. I'm always going to start and put my convention, in this case, in the upper right-hand corner. And for this problem, you'll notice that we have pound, inches. So our units are going to be English units, all right? So as far as givens, I like to, again, get my mind in. Gravity is equal to 32.2 feet per second squared. All right, that just make sure that that's top of mind as I'm doing my problems. I know that the weight of my pulley is 12 pounds. Okay, we also know the weight of each one of the blocks. So the weight of A is equal to 5 pounds. The weight of B is 10 pounds. Okay, and they show those clearly. And then we also know, as far as the pulley, I'm going to kind of write it over here, and K, radius of gyration, is equal to 8 inches. Okay, now, because we are in English units, and we have, for instance, our gravity in feet per second squared, we want to make sure that any distances we have are also in feet. So right now, this radius of gyration is in 8 inches. We would just divide by 12. I'm not going to have you write out that conversion anymore. We're just going to divide by 12, and that's going to be 0.667 feet. Okay, so K is equal to 0.667 feet. So these are, this is the pulley. Okay, this is the pulley. Those go together. Right now, what we need to find, all right, what we need to find is the angular acceleration of the pulley, okay? The straight line acceleration of that block A, and the straight line acceleration of block B, okay? All right. So the first thing we're going to do is we're going to draw our diagrams, okay? So number one is going to be our diagram. All right. Now, I'm not going to draw these as circles. What I'm going to do is I'm going to draw them as like kind of lines on the radius. So you'll kind of see. So I'm going to start over here. This is going to be B over to A. And then off center, okay? This is going to be B. This is going to be A. Off center, this is going to be our G, our center of gravity, or the center of rotation, if you would. Okay. And going down from that center, this force is going to be W of that pulley, which is equal to 12 pounds. I think for this is for G. Now, the radius out to point B is 0.5 feet, okay? So again, we have to have everything in feet. And if we look at the problem, this is identified as 6 inches. So that's going to be 0.5 feet, okay? And then we have this radius as 10 inches out to A. So that's going to be 0.833 feet, okay? So make sure all of our units are in feet for distances and not inches. Okay. Now at B, force-wise, we have the weight of B going down, and then at A, we're going to have the weight of A going down. So B is 10 pounds. Okay. 10 pounds. And A is 5 pounds. And then there is a reaction force because there is a, you can see there's like a little bearing or a little support here at G that would keep that pulley from falling or, falling down. Okay, so force-wise on the left-hand side here, I think we're all set. We're going to set that equal to our acceleration and moment of inertia, right, over here. So we're going to draw that very same arrangement. So this is going to be our B. It's going to be our A. But this time, we're not going to put the forces going down just yet, okay? I'm going to first draw my center of gravity or center of mass. I know that I have half a foot from G out to B, and I've got 0.833 feet from G out to A. Now, I need to determine which way this is rotating, okay? When I look at it. Now you might say, wow, if it's 10 over here, it's gonna go in a counterclockwise direction. But remember, this is only a half a foot over or 6 inches over, and this one is 8 inches over. All right. I'm sorry, 10 inches over. So what we need to do is we need to determine what is the moment on either side so we know which way, clockwise or counterclockwise, this is actually going. So to do that, we're simply going to determine where is the larger moment, okay? So if we compare the moment on either side over here, so for instance, if I sum my moment around G, okay, and I'll say equal to 0, that's totally fine because it's just kind of the normal way that we do it. I'm going to look at B first, so I have my finger on G, and I'm going to rotate that 10 pounds times 0.5 feet, okay? And it is going to go in a counterclockwise direction, so that'll be positive. If I go around G again and I pull in the direction of my A, my 5 pounds, I am going to have a negatively directed moment. It's going to be 5 pounds times 0.833 feet, okay? Equal to 0. So if I put this one to the other side and I multiply these out, this one is B, this one is A, right? The moment B, the moment A. So if I take this is going to be 5 pound inches. I'm just going to use the number right here. It's going to be equal to, because I'm going to move this to the other side. It's going to become positive. And this is going to be like 4.15, okay, on that side. And so this represents A, this represents B. B is a larger moment value than A. So that means that B will be accelerating down with its mass. Now remember, this is not force on this side. This is going to be the mass times acceleration. So this is going to be mass B times acceleration B, straight line acceleration B. And if this is rotating around, so if this is pulling down because that has the greater moment, then A is going to go up. Okay, so this is the direction that it's moving or accelerating. So this one is going to go up on the right-hand side. So this is going to be the mass of A times the acceleration of A. Okay. Because that is the direction that each one of those straight lines are going, then that means that we are rotating, the pulley is rotating. So this is going to be I pulley, alpha pulley. Okay, so the pulley is rotating in this direction. Okay, so this is going to be our rotational inertia times that angular velocity, and that's going to be our angular momentum. Okay. Now, this was kind of just for, so that we could confirm that direction. So what I'm going to do is I'm just going to delete, I'm going to erase this so that I have more room for the stuff that I want to write out. Okay. So those are my little notes for you. All right. You can keep those notes there if you did, but I just wanted to have a good explanation for you on that. Okay. So now what we want to do is we know that we're going to need these straight line accelerations for our motion equation. So we're going to see if we can actually calculate those first. So I'm going to determine the accelerations. And that's going to be the acceleration at A, and the acceleration at B. Okay, we're going to see if we can get those kind of at least semi figured out. Now, we know when we look across here, and we're just going to draw kind of the illustration kind of up here, but we're going to eliminate the masses. So I'm going to have A on this side and B on this side, and my center of rotation is right about here. We know that our angular acceleration is going in a counterclockwise direction. We know that B is accelerating down, so this is just going to represent only the acceleration of B. We know that A is going up, so its acceleration is going to be up. And then this is G. And the distance out here, the radius out, this is going to be radius B. We know that to be equal to 0.5 feet. And then radius A is equal to 0.833 feet. Kind of sneak it in there. So as this rotates around, these accelerations are perpendicular to the radius of rotation, which means that they are a form of a tangential acceleration. Okay, so these are tangential accelerations. Okay, and we know that tangential acceleration is equal to, if we go back to our sheet, the angular acceleration times the distance away from that center of rotation. So times that radius. So we know that this is going to be times that. So we can say that acceleration B over here in its tangential form is going to be equal to radius B times the angular acceleration, which would be of that pulley. Okay, we've been calling it that alpha P. So we can say that AB then is going to be equal to 0.5 times alpha P. And that's as far as we can go. We don't know what that is, but it gives us a form of that acceleration that we'll be able to use in the motion equation coming up. And then we're going to do that very same thing for acceleration at A. This is going to be the radius at A times the angular acceleration of the pulley. So our acceleration at A, straight line acceleration at A, is going to be 0.833 times alpha P. So we're going to leave it in that form. Okay, we're going to leave it in that form. Okay, so let's continue on. The next thing that we're going to do, okay, we are going to calculate the moment of inertia of that pulley, or the rotational inertia of that pulley. So step number 3 here is going to be moment of inertia of that pulley. So we know that I, for that pulley, is going to be equal to mass times the radius of gyration squared. This is, we had already established that this is not an even cross section of a simple shape, so we can't use one of those canned equations. We're going to have to use that radius of gyration value that they gave us. Okay, now to get it, we need to know what the mass is, but we don't know what the mass is. But what we do know, right? What we do know is that we know that mass is equal to weight divided by gravity. Okay, we know the weight of that pulley. We know the weight of that pulley is 12 pounds. And if we divide it by 32.2, we're going to get the mass, right? So we're going to use that value right here in the equation. All right, so we're going to say 12 divided by 32.2, it's going to represent the mass, times the radius of gyration. Now, if we go back, remember, it gave it to us in the problem as 8 inches. We can't use that. We have to have it in feet because we need all of our units to be consistent. So it's going to be 0.667 feet. And we have to square that value. Okay, don't forget to square it. So our rotational moment of inertia of that pulley is going to be 0.1658. 1658. Okay. This will be the value that we use now in our very next step, which is going to be step number 4. And this is going to be our motion equation. Oops. Okay. All right. It's going to be kind of long, so I'm going to start over here. So we're going to use the sum of the moments around that center of mass G. So if we look back at our diagram, we're going to have our finger on here. So this is that left side. We're going to sum our moments, and then we're going to set it equal to the angular momentum. So the first part of that is going to be, I should put my P's in here, the rotational moment of inertia of the pulley times the angular acceleration of the pulley. Plus, now these are going to be our translational. So if we look here, we have straight line acceleration due to B. So we're going to do that one first. So that is going to be, and I should say, it's offset from the center of rotation. So we are going to have a mass B times acceleration B times distance B perpendicular to that center of rotation. And that distance is going to be the radius, okay, because it's perpendicular back. And then we're going to do the same thing for our A. So this is going to be plus mass A, acceleration A, times distance A perpendicular. Okay. Questions so far? All right. Now, the other thing I want to identify here is you'll notice that these are both positive. If we look and we put our finger on G, these are going to rotate, both of them, in a counterclockwise direction, which is positive according to our convention. So they both remain positive. Okay, so we're going to start over here and we're going to sum our moments first on the left-hand side. So putting our finger on G, we're going to first pull in the direction of B. That's going to be 10 pounds times 0.5, and it's going to go counterclockwise. So we're going to have, and I'm going to start way over here because this is going to get kind of long. So positive 10 times 0.5. Okay. Then we're going to do the same thing, put our finger on G, pull in the direction of A. That's going to go that's going to go clockwise, so that'll be a negative direction, 5 times 0.833. This will be negative 5 times 0.833. Okay. Now, if we look back here, the W, the weight, and the reaction are going through that center of rotation, and that's what we're summing around. So those are not included in our moment side because they don't cause rotation or they're not offset, right? Okay, so now we're going to set that equal to, and our moment of inertia is going to be the 0.1658 times alpha p. Okay, that's unknown. Plus mass of B. We don't know the mass of B, but we do know mass to be equal to weight divided by our gravity. We know the weight of that block is 10, and I'm only going to put pounds here so we kind of know why it's there. And we're going to divide that by 32.2. That's the mass times the acceleration of block A. If we go back over here, we know that to be equal to 0.5 alpha p. So 0.5 alpha p, that's the angular velocity of our pulley, times the perpendicular distance, which is the radius. So that's going to be 0.5 again. Plus the mass of A. The mass of A, it's going to be its weight, 5 pounds, divided by 32.2, times the acceleration of A, 0.833, times alpha p, 0.833 alpha p, times that perpendicular distance, which is the 0.833 value. Okay. So you will notice here that our unknowns are the angular velocities of our pulley. So we're going to, multiply these out, and then we'll be able to combine each one of these. Okay. And that's our only unknown. So we'll be able to calculate that angular velocity here. So go ahead and do the math. I'm going to kind of do it on the side here, and and it's important to make sure that you get the same answer as I do. Are there any questions on this equation right now? Hopefully the numbers all make sense. Okay. All right, I'm going to go underneath. This is going to be So it might take you a little while to get it, but this would be the answer. So you want to compare once you get yours figured out. All right. Let me know if you get it. Oh, you got it? Okay, perfect, Brooke. Thank you. Everybody a chance to get caught up here. So this is our first final answer that they were asking for. One of the things that we wanted to find was the angular acceleration of that pulley. Okay. Now this is a positive value, so it's speeding up, which makes sense because that 10 is going down. It should be going faster and faster, right? Okay. Does anybody need extra time to get the number here? Right. So if we look back, the first one here, angular velocity of that pulley was what we needed to find. Now we need to find the two straight line values. Oh, I'm sorry, Tyler, you got point. Yeah, I'm sure it could be a little bit of rounding. Or wait. Oh no, mine is 0.237. I'm so sorry. I think I copied it wrong. I did get points. Brooke, did you get 2.37 or very close to that? I'm
I
sorry.
two
I
point
missed.
38.
Oh, okay. Yeah, I'm
It's
sure it's
close.
right there. Yeah. So now we're going to use that value down here on that first page. We calculate those straight line values. So we're simply going to take zero point 0.5 times that angular acceleration and then 0.833. Okay. So this is going to be step number 5. We're going to get those straight line accelerations. Okay. So that means our acceleration at A is going to be equal to 0.833 times alpha P. So 0.833 times 2.39. And our acceleration A. Now, this is straight line acceleration. So the units are going to be 1.974. And it's going to be, oh, you guys tell me, what would the units for acceleration be here? I know what they are. I want to make sure you guys know what they are. What would my units for acceleration be here?
Feet per second squared.
Feet per second squared. Thank you. So feet per second squared, and it's going up. It's going up. So this, and that's consistent with our illustration over here. Okay, so we have the direction. So that's a final answer, and that takes care of our second value. And now we're going to use this equation here to get the acceleration at B. And this one is going down. So you should get 1.185 feet per second squared. Make sure that the final units are in here. Don't leave those off, all right? We have not been putting them in the problems because things like this up here would get like so long. You'd have to have a couple lines to try to get all that in and then cancel out and stuff like that. And as long as we're, really diligent about the beginning here and making sure that all of our units are consistent with the units that you know, are the units of measure, will be good, but we have to put in the appropriate units, in this case for acceleration, feet per second squared, in the final answer. All right. So any questions on this problem? That concludes it. All right, then what I'm going to do is I'm going to stop the recording here. We'll do our last problem.